Greetings ACT, Commander King here, taking a look at 3 different types of compounds and really identifying different features about them. So we're going to kind of review all of these concepts that we've been learning. I've got NaCl here, and we can actually talk a lot about NaCl now. So, we know this is salt, but we also know that it's an ionic compound. How do we know it's an ionic compound? Well, good question. There are a few ways. We can look at our periodic table and remember there's a metal non-metal line, and we know Na is a metal. It's to the left of the metal non-metal line, and Cl is a non-metal. And so when you have a metal and non-metal, generally you have an ionic compound. We can also take a look at the difference in the electronegativity of the elements and see that, well, Cl is really good at taking electrons or pulling in electrons or being attracted to electrons, and Na not so much. So we know this is going to be a give and take kind of relationships. And once we know that, we can actually predict what's going to happen. So what will happen is Na, we take a look at the valence electrons. Na has 1 outer electron. Cl, on the other hand, has 1, 2, 3, 4, 5, 6, 7. And what you might imagine happening based on the octet rule is they all want that full outer shell. Cl, very good at taking an electron, takes one from Na. Na loses its electron, becomes positively charged. Cl now has those 8 outer electrons, has gained an electron, and when you pick up an electron, which are negative, you become negatively charged. Okay, and so that's just the structure. So we've done 3 things. We've taken a look at whether it's ionic. We were able to draw the Lewis-Dot structure, and that's it so far. All right. Now I want to predict if can this be conductive, and the answer is, well, yeah, ionic compounds can be conductive, especially when they're placed in water or when they're a liquid of some form. And the reason is, if we think about this as a 2 ends of a conductivity test, like the 2 ends of the metals, well, the electrons on the negative end are trying to jump across to the positive end, but they can't because it's too far. But these ionic compounds kind of help form a bridge. You can think of these Na plus ions all being in here. And this allows the electrons to kind of have a bridge to move across. And so that's why things conduct electricity, mostly because of charges, right? The charges are the key. So does this conduct? Absolutely. The electrons are able to move through and electricity can flow through. All right. Now, we want to predict, okay, does it have high or low melting points, ionic compounds? In other words, is it going to be hard to separate the atoms and make them into liquid when they're solid? And again, to think about this, we want to look at their charges. And we know if you have Na plus and Cl minus, okay, opposites tend to attract. Okay, and if they attract to each other, if I try to take them apart, it's going to be difficult because they're trying to attract to each other, right? They're attracted because of the opposite charges. I'm trying to pull them apart, and I'm not able to do so. Okay, so in addition to conducting, which I figured out, they also have high melting points, because high melting points means it takes a lot of energy to melt them, and they're very hard to pull apart. All right. And finally, I want to predict what happens when they dissolve in water. Well, ionic compounds, when they dissolve in water, the water molecules surround each of the charges. And so you have this Na plus and the Cl minus, they separate, and the water molecules just surround them, with the oxygen pointing towards the positive end because the oxygen is partially negative. And in the Cl, it's the opposite. The hydrogens, which are partially positive, point to the Cl minus. Okay, so again, when ionic compounds hit water, they break down, definitely. All right, great. Let's look at HCl. In HCl, both of these are nonmetals. Remember, hydrogen being a nonmetal, moving to the right side of the periodic table. And so we consider this a molecular compound. However, if you look at the difference in En, the difference in En is very high. I think greater than 2, maybe? No. Maybe about 1.4, I forget exactly. So we know not only is this molecular, but it's polar molecular, which means they still share electrons, but they share unequally. Okay, they share unequally. And what HCl will do is H, with its 1 electron, will share with the 7 from Cl. And this makes H happy because H only wants 2 outer electrons. It's only got 2 it only needs 2 electrons in the first ring, so that's happy. And Cl needs 8. Here's 8, so Cl is happy, and they're kind of forming a good bond. But Cl is more electronegative, which means it's better at pulling electrons towards it. And so these electrons are kind of shifting towards the Cl minus, because the Cl, because it's better pulling. And so what we do is we label this with a partial negative charge and this with a partial positive charge. Okay, so that's what will happen here. Partial negative, partial positive. Okay. All right. I'm going to kind of skip this part in terms of conductivity and melting point because and dissolving, because it gets pretty confusing with polar molecular. A lot of different things can happen. So I'm going to jump straight to Cl2 and see what's going on here. So Cl2 just has 2 Cls, molecular compound. Both are non-metals, the Cl and the Cl, that are bonding together. The electronegativity difference is 0 since they're the same element. And in this case, well, we have 1 Cl with 7 electrons. 1, 2, 3, 4, 5, 6, 7. And we have another Cl. Let's use a different color. This different Cl also has 1, 2, 3, 4, 5, 6, 7, forming a bond here. And all of them have 8 electrons around them now, so they're happily sharing, and they share equally. In other words, there are no partial charges because what these Cls are just as good as the other one as pulling electrons in. All right, so let's talk about the conductivity. All right, so let's say I draw my same kind of thing. My electrons are trying to jump across, but this time instead of charged particles, all I've got is a bunch of Cls. All right. And so these charges, these electrons, don't have anything to jump to. They can't get across. There's like a wall here. It's just as if there were nothing there. There's nothing to jump across, and so hence there is no conductivity here. Okay. And if we want to think about melting points, well, let's think about whether anything would make this hard to pull these Cl from another Cl2, like this. If we think about these as compounds, well, there are no charges. There's no attraction. It's like if I have this pen and this graphing calculator here, I'm like, well, that's not too hard to take apart. There's no attraction between them. It's not like they're sticking to each other like a magnet, like an ionic compound would. And so these generally have low melting points. Okay, very easy to melt because it's easy to separate the molecules in there. All right, one final note. You want to think of molecular compounds like oil. Oil is made up of a lot of molecular compounds, and if you think about adding oil to water, you know that the oil generally floats on the top, and the same thing happens with molecular. It floats, and that's because there are no charges, and no charges or no partial charges means the water molecules don't really like interacting with the ones without charges. And so what they're going to do is they're going to kind of form their own layer and not interact with the water molecules at all. Okay, so a quick review about a few different compounds and their properties. King out.